In this set of notes, we're basically going to build off of what we did in the 6.1 notes by talking about the concept of a Taylor polynomial. So we're still dealing with this idea of approximating values of a function, just like we were doing in the previous set of notes. So we're going to talk about what this idea of a Taylor polynomial is, along with this idea of a Maclaurin polynomial, and we'll see that a lot of this is very similar to what we were just doing in the previous set of notes, and actually builds directly from what we were doing in the previous set of notes. Okay, so what were we doing in the previous set of notes? So let's look at our motivation section here. So remember from the 6.1 notes, we were talking about linear approximation or the linearization of a function. So we learned this expression was the linear approximation or linearization of a function at x equals a. And essentially, the idea here was this approximation. Our function L of x can be used to approximate the value of our original function for values of x near a. And the whole idea was this is really nice in cases where our original function is not very easy to work with, especially without a calculator. But the linear approximation, this L of x, is usually easier to work with and allows for a pretty good approximation of the original function. So just to kind of bring back what we were just doing here, the whole idea here, this was page 2 from our 6.1 notes, is that here we have some function f of x, and at some point that we care about, or some point that's relatively easy to work with in terms of plugging it into things, we can talk about the line tangent to the function at that point. So we've got this straight line, and we've got the slope of this straight line, the slope of the tangent line, f prime of x. And the idea is, if we are relatively close to that point, in this case x equals 1, then we can see that the function in blue and the tangent line in red act pretty similarly near, in this case, 1. So for values close to 1, again in this specific case, the tangent line is a pretty good approximation of the original function. And we can use the tangent line, this thing, to get a pretty good idea of how the function is behaving near 1. So if we wanted to plug in, I don't know, 1.2 into our function, but for one reason or another that's difficult to work with, we can instead figure out what the function's tangent line is doing at 1.2, and that would give us a relatively good approximation of the function's behavior at 1.2. That's still carrying on here, so we're still talking about that idea. And these were some of the examples that we talked about in the 6.1 notes, this idea of how do we find the cube root of 5.5, or the sine of 3, or the natural log of 6. So this works pretty well. But what if we can get an even better approximation than linear approximation, while still working with a function that's relatively easy, or easier at least, than the original function? So this is where we get into this idea of the Taylor polynomial. And the general form of the Taylor polynomial basically allows us to get as nice of an approximation as we want. So to introduce Taylor polynomials, let's talk a little bit of why linear approximation works so well. So the main reason that linear approximation works so well is because of that idea of that first derivative, that slope of the tangent line. Remember, this linear approximation is built on this idea of the tangent line itself, and specifically the slope of the tangent line. Remember, I keep reiterating this, the slope of the tangent line is the same as our derivative of our function at a specific point. So the slope of the tangent line at a is the same thing as the first derivative of the function at a. And that's really the key for why linear approximation works so well. The linear approximation, that tangent line, is the unique line such that the linear approximation at a is equal to the function value at a, and the first derivative of the linear approximation, the slope of the tangent line, is equal to the slope of the function at a, that instantaneous rate of change. So how do we increase the ability or the accuracy of our approximation? Well, the way we do that is by increasing the number of higher order derivatives that are the same. So here the first derivatives are the same, but what if we found another function where not only the first derivatives were the same, but the second derivatives were the same? Or even further, maybe the third derivatives are the same. Basically, the more derivatives that are the same between the the approximation function and the original function, the better the approximation will be. And these polynomials, these additional approximation tools, are what we call Taylor polynomials. So Taylor polynomial is basically the name we give to a structure of a certain type of polynomial. So we can talk about the first degree Taylor polynomial, the second degree, the third degree, the fourth degree, etc. If we want to generalize this expression and talk about the nth degree Taylor polynomial, where this again is like 2 or 3 or 4, etc., the nth degree Taylor polynomial of a function at x equals a is expressed in this form here, which can kind of seem a little bit overwhelming to start with. It looks like there's a lot of stuff going on here, but there is a nice pattern to this expression, and I think that makes it a little bit easier to see and fill in as we actually use this sort of thing. So we also have this in summation notation. If you're not super familiar with summation notation, don't worry too much about this expression. But if you've seen this expression before or you're comfortable with summation notation, this is the same expression as this, just in a more compact form with that type of notation. The one thing I do want to mention here that you might not have seen, especially if you haven't taken, say, statistics or like set theory, is this notation here, this 1 exclamation point, 2 exclamation point, 3 exclamation point, n exclamation point. I've got a note here for that. N exclamation point, that exclamation point is a certain type of operation. It's in math, it's a factorial. So n exclamation point is read as n factorial. And for our purposes, we're assuming n is a positive integer. So like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. And the way that we compute n factorial for our purposes, it can get more complicated than this, but for our purposes, n factorial is we take the integer n and we multiply it by all of the integers less than n all the way down to 1. So for example, 7 factorial is 7 times 6 times 5 all the way down to times 1. And factorials get pretty big pretty quickly. So 12 factorial might be a little too big for your calculator. 13 factorial is enormous. 52 factorial actually has its own name. It's called Graham's number. And it's this almost incomprehensible huge value. Look up on like YouTube or Wikipedia Graham's number. It's 52 factorial. It's really interesting if you're into that sort of stuff. But I'm getting off track here. I like factorials. You can get more complicated with factorials by doing it with non-integer numbers, but for our purposes, for this course, we're basically going to see it in this expression in the Taylor polynomial. Now, the pattern that I want to mention here is in the pieces of this sum. So we have this piece. Notice each of these is added to everything else. And here's the pattern that I want to point out. So this is just our function f of a, or f at a. But once we get past that part, the rest of the pieces in this sum follow a nice pattern. This is the first derivative. This is 1 factorial. This is x minus a to the 1. Everything involves a 1. The third piece of this sum, second derivative, 2 factorial x minus a squared. Everything involves a 2. The fourth piece here, third derivative, 3 factorial, x minus a to the third. So if you can kind of remember that pattern of, except for this piece, each of these just involving everything has a 1, everything has a 2, and a 3, that's one way to fill in or remember this structure of the Taylor polynomial. It's got a nice pattern to it. And usually we denote a Taylor polynomial as t sub n of x. So if this is like the 8th degree Taylor polynomial, this is t sub 8 of x. Or the 2nd degree Taylor polynomial, t sub 2 of x. That sort of thing. Now, we'll sort of see this in the examples that we're going to go through on the next couple pages, but there is a little bit of a trade-off here. Basically, the idea behind the Taylor polynomial structure is the more degrees you have, so the bigger this n, the larger this sum is, and the better the approximation is to the original function in terms of its behavior. Now, once you're calculating like the 8th derivative, the 9th derivative, you might be like, well, I'm doing just as much work trying to calculate this Taylor polynomial as I would for the original function. Why am I trying to even approximate it if I could just do as much work calculating the actual number from the actual function? And that's definitely a valid concern or a valid critique of this to bring up. Taylor polynomials, especially for our purposes, are usually, in most cases, at most, the 3rd degree Taylor polynomial. So we usually don't go much beyond this. Sometimes we'll do 4, sometimes we'll do 5 if the derivatives are relatively easy. But for most cases, we usually kind of cut it off at 3. I think I have an example that we actually do 4. Let me just check. Yeah, so I have an example where we're doing the 4th degree, so I'm kind of lying here. But we'll see that the derivatives in that case are relatively easy, so it might be worth getting that extra boost in approximation. But in most cases, our Taylor polynomials have a relatively small degree, that n is relatively small, 2 or 3 or 4. And when we start looking at these different Taylor polynomials, some of them do actually have different names in terms of other things you might call them other than like the 3rd degree Taylor polynomial or the 2nd degree Taylor polynomial. So this one here, this is like the 0th degree Taylor polynomial. It's not used that often because its approximation ability is not that great. It's just our function value at a. So it doesn't really give us, if we are looking at values a little bit beyond a, it doesn't really give us that good of an approximation. So we don't really use that one too much. This one we actually use quite a bit. So this is the 1st degree Taylor polynomial. I have it written in the same structure as up here. So the 1st degree Taylor polynomial, is just this. So f of a and then everything involving 1, that's the nth degree, the 1st degree. So I have this written down here, but if I write this without the extra pieces, so f of a plus, well, 1 factorial is just 1, and x minus a to the 1 is just x minus a. So if I write this without those little extra pieces, oops, put my first derivative in here. Notice what this is. This is exactly what we were doing in the previous set of notes. This is our linear approximation. So the linear approximation is actually the 1st degree Taylor polynomial. We just didn't call it that because we didn't know what Taylor polynomials were yet. But this is linear approximation. So another name for linear approximation, or the linearization of a function, is the 1st degree Taylor polynomial. The 2nd degree Taylor polynomial, notice this includes everything up to everything involving a 2 in that expression. That's sometimes called quadratic approximation. And then another pretty common one that you'll see, again, there's a trade-off you start getting between calculating a bunch of higher order derivatives versus just dealing with the original function. This one, the 3rd degree Taylor polynomial, is our cubic approximation. So if you do, or if you have heard those terms before, that's what they're referring to, just sort of the first 3 most commonly used or lowest degree Taylor polynomials. So again, the linear approximation, the 1st degree Taylor polynomial stops at everything involving a 1. The 2nd degree polynomial stops at everything involving a 2. The 3rd degree polynomial stops at everything involving a 3. And so these work as good approximations, and the approximations get better the more degrees you have, because the nth Taylor polynomial of our function is going to have the same first n derivatives as the original function, which means that the higher the Taylor polynomial is in terms of its degree, the n, the better the polynomial is going to hug the original function and the better the approximation of its behavior it's going to be. Now, as always, I like to do a visual of this, and we'll see a couple of visuals here in a second when we do some examples. But let's look at this picture here on page 3. So the function here in blue, in the solid line here, is this, f of x equals e to the x. So maybe that's not the easiest function to work with in terms of finding specific values for different values of x, especially if you don't have a calculator. So like if I wanted f of, I don't know, 4.4, that would be e over 4.4, which might not be the easiest thing to calculate without a calculator. Or I should be maybe a little bit more specific. If we wanted to approximate f of x values for x values near 1, if I wanted, say, f of, I don't know, 0.99, that's e over 0.99. Again, maybe not the easiest thing to calculate without a calculator, but I could use a Taylor polynomial to get a better idea of, or a better approximation of this function without actually having to use this original function. So I will uncolor that just so the rest of this is a little bit easier to see. So I have here plotted along the original function in blue three different Taylor polynomials, different approximations: the linear, the quadratic, and the cubic. So again, the first degree Taylor polynomial, the linear, the second degree Taylor polynomial, the quadratic, and the third degree Taylor polynomial, the cubic. So the first degree Taylor polynomial is in red. That's our linear approximation. We can see that's just this straight line. It's the tangent line. Let me draw that a little bit better. That's the tangent line to our original function at x equals 1. Notice here's x equals 1. The quadratic Taylor polynomial is here in green. Notice it looks like it hugs that blue function a little bit better, a little bit longer than the red function does. It's a bit nicer of an approximation further out from 1. And then finally our cubic approximation, it's a little bit harder to see on here, but it kind of looks like this. And that looks even better in terms of hugging that blue line and staying close to it for values of x near 1. And if we were to continue this pattern, 4th degree, 5th degree, 6th degree Taylor polynomials, the better our approximations would get. So we're going to do a couple examples here on the next few pages, but one other thing that I want to mention here, just because it is a name or a term that you might hear, is a Maclaurin polynomial. So a Maclaurin polynomial is the same thing as a Taylor polynomial, but it's basically a Taylor polynomial when your a is 0 or when x equals 0. So when you're approximating around the value 0, it's just a more specific name for this type of function. So it's just a more specific version of the Taylor polynomial, named after, I think he was Scottish, Colin Maclaurin. Brooke Taylor was a English mathematician, and they did a bunch of other stuff as well. And technically the Taylor polynomial, I think, was developed originally by somebody else, like a lot of things in math. The thing it's named after was developed by multiple people or completely different people at a different time. But that's what we're working with here. So the thing about these polynomials, and I remember when I was taking calculus, I found these to be kind of overwhelming at the start because they can seem a little daunting. But the trick is to go slow, remember the structure, and then you'll see that there's this nice sort of pattern to them, and it's less daunting once you sort of take it slow the first couple times and recognize that pattern. So let's take a look at a couple examples here. Starting here on page 4. So we want to find the third degree or cubic Taylor polynomial for this function, f of x equals sine of x, about x equals 0. So I know I want to find a Taylor polynomial, and specifically I want the third degree Taylor polynomial. So the first thing I'm going to do before I do anything else, and I recommend doing this as well when you're practicing with these things or on an exam even, is I'm just going to write the form of the third degree Taylor polynomial, and then I'll fill it in as we go. So I'm going to go back up here, and we kind of are, well, we saw it here, but just to emphasize it with this, if I want the third degree Taylor polynomial, I'm going to extend this pattern until I get to everything in the sum involving a 3. So basically this expression here, like we have at the bottom of page 2 right here. This is my cubic approximation, or my third degree Taylor polynomial. So I'm going to write down my structure, then I'm going to fill everything in. This is going to be equal to f of a plus f prime of a over, now here's my pattern, that's the first derivative, so this is going to be 1 factorial times x minus a to the 1. Let me rewrite this derivative sign so it looks more like a apostrophe than a 1. Plus, now everything's going to involve a 2. This is the second derivative at a. This is 2 factorial. This is x minus a squared. Then I want the third degree Taylor polynomial, so I'm going to have one more piece to this sum where all of those components are going to be involving the third thing. The third derivative at a, 3 factorial x minus a to the third. So there's that pattern. Now there's a couple things I need here. I need, of course, my a. I see it here, 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 here. And I need my function and its derivatives at a. So function, first derivative, second derivative, third derivative. So let's start with a. Now this is very similar to the a, or it is the same thing as the a when we were doing the linear approximation. It's the specific value of x that we care about. So here, since we're finding this polynomial about x equals 0, that's the same thing as saying the a in our expression is equal to 0. So here, a equals 0. Now, in terms of our function and its function and derivatives at a, we're given our function here as the sine of x. So f of x equals the sine of x. Now I know I'm going to have to go all the way up to the third derivative here, so I'm just going to write down the first 3 derivatives of the sine of x. So f of x equals the sine of x. F prime of x is equal to, what's the derivative of the sine function? Cosine. My second derivative is the derivative of my first derivative. Remember our higher order derivatives. So the derivative of cosine of x is negative sine of x. And then I need one more. I need my third derivative. Third derivative is the derivative of the second derivative. Derivative of negative sine of x is negative cosine of x. And now what I also need is I need all of these function values and the derivatives at a. So for each one of these things, I'm going to plug in my a, my 0. So f of 0 is the sine of 0, which is 0. For preparation for like an exam or something, I would recommend looking at a unit circle when you're doing this rather than using your calculator, just so you get used to reading a unit circle or remembering sort of those big cosine and sine values for like 0, 1, pi, pi over 2, pi over 3, pi over 6, that kind of thing. Just for practice. This is the first derivative at 0, so the cosine of 0. Cosine of 0 is 1. negative sine of x, that's my second derivative, so that's f prime prime at 0, or the negative sine of 0. Well, we already said the sine of 0 was 0, negative 0 is still just 0. And then my third derivative at 0 is going to be negative cosine of 0. And we said cosine of 0 is 1, so negative cosine of 0 is negative 1. Now, all we need to do is plug this information into this structure. So we don't have an x, that's sort of our stand-in, that's just going to stay where it is. But we have these a's, we have these derivatives, so let's plug everything else in here and see what we get. So the third Taylor polynomial is going to be f at a, which we said was 0, plus, now I'll do this part, the first derivative, which we said was 1, over 1 factorial. 1 factorial is just 1, times x minus a is 0, all raised to the 1. So I'm just plugging in my components into that piece. Plus, now let's do this one. The second derivative, 1, over 2 factorial. 2 factorial is going to be its value 2 times all of the integers down to 1, which is just 2 times 1. And that's going to be times x minus 0 squared. And then finally, I have the third derivative, which is 0, over 3 factorial. Oh, sorry, I'm getting my derivatives mixed up. Ignore all of that. Let me start over. Sorry if I'm confusing everybody. Let me just start over here. Okay, so this is correct. This is the sign. Sorry about that. Sometimes it's good to leave in our mistakes, though, because then we can kind of backtrack and see where the mistake was made. All right, let's try this again. So let's do this correctly this time. The first derivative is 1, so we did that one all right. 1 over 1 factorial is 1, times x minus 0 to the 1. Here is where I think I messed up. So this is now my second derivative. My second derivative is 0. So this should, if you were following along earlier and you're like, wait, I think you did that wrong. You're correct. I did that wrong. That's 0, my second derivative, over 2 factorial. 2 factorial is 2 times 1 times x minus 0 squared. Plus, now this is looking a little bit better. Here's my third derivative over 3 factorial. My third derivative is negative 1. So 3 factorial is 3 times 2 times 1, all times x minus 0 cubed. Sorry about the mistake. Hopefully that cleared that up when I redid that. All right, so that still kind of looks messy, but notice we have a couple things that are going to end up being 0. This thing, of course, in this sum, that's going to be 0. And here we have a 0 over something. This whole big product is going to be 0. And the only two pieces are going to be this plus this. So this is actually kind of a nice, tiny little third degree Taylor polynomial. This is going to be 1 over 1 is 1 times x minus 0. X minus 0 is just x. So that whole piece is just going to be x. Plus negative 1 over 6, right? 3 times 2 times 1, so I'm going to write that as minus 1/6 times x minus 0. X minus 0 is x cubed. So this thing is my third degree Taylor polynomial for the sign of x, about x equals 0. So two things to notice. One, notice this doesn't have a sign function in it. We've completely eliminated the trig, which is really, really nice in a lot of cases when we're trying to approximate. We don't have to worry about plugging things into a sine function or cosine function. Now we have a relatively easy function here to work with. So that's one thing. We've eliminated the trig, which is always nice for calculation. The second thing, just to reiterate this definition, is since we were finding the Taylor polynomial about x equals 0, another way we could have said this is find the Maclaurin polynomial for f of x equals sine of x. Because remember, the Maclaurin polynomial, it's assumed by definition, by this specific name for this polynomial, that the thing that we're finding this about is 0. So another way that I could have phrased this is find the third degree Maclaurin polynomial for f of x equals sine of x. And by saying Maclaurin polynomial, this is implied. So I'm just going to write on here, this is also a Maclaurin polynomial. All right, so what do we do with this? So we found this Taylor polynomial, that's great, but what can we do with it? Well, let's use it to approximate a value for our original function. So our original function is the sine of x. What if we wanted to approximate the sine of 0.1? Now, of course, if we have a calculator, we don't have to approximate this value, we can just calculate it. But let's pretend we don't have a calculator and see if we can get an idea of what this would be using this. Okay, so how do we do that? So to approximate the sine of 0.1, notice that our argument here is like our x, right? Our original function is the sine of x. I'll just write it here from above. Here, our x is 0.1. So if I want to use this thing to approximate the sine of 0.1, I'm going to plug in this x, this 0.1, everywhere I see an x in my Taylor polynomial. So in other words, I'm going to use the third Taylor polynomial at 0.1. And so everywhere I see an x up here, I'm going to plug in 0.1. 0.1 minus 1/6 times 0.1 cubed. Now I used a calculator to calculate this out, but just to show you what this number is so we can compare it to this actual sine calculation, if we were to use a calculator or something to figure out this value, we would get 0.099833333 repeating. That's my approximate value of the sine of 0.01, or sorry, the sine of 0.1. Because we can, let's also write down the actual value of this sine of 0.1, just to see how close we are. So doing this on my calculator, I get 0.098833417. That's a pretty good approximation without having to use any trig expression in that calculation of that approximation. So we're approximating this with this, which is pretty good. Pretty good approximation. Let's look at this visually, because again, I think visualization helps a lot with this sort of thing. So what's our original function? Our original function is this sine of x. So if I go to Desmos and I plot the sine of x, I get this. Here's my sine wave in blue. That's my sine of x. Let's also plot our third degree Taylor polynomial. I'll plot that in orange. So notice it definitely has a different shape overall than my sine function, but for values of x near 0, near a equals 0, notice how close those two functions behave. They're very similar. And if I zoom in, we can see it starts to deviate the further you go away from 0, but even zoomed in this much, near 0, these functions are behaving almost to the point where I can't differentiate them without making one invisible versus the other. Now, in terms of the approximation, so we wanted to approximate the sine of 0.1. So where is the sign of 0.1? Well, our x value is 0.1, our y value is the sign of 0.1. This is going to show up on my blue graph, believe it or not. This is the actual value that 0.99833,417. Desmos rounds a little bit more than I did, but that's my actual sign of 0.1, that y coordinate. This, over on the side here, this is me plotting. Here's my x, that 0.1, and here is my approximate value of the sign of 0.1. And let's see what we get. I'll plot that in orange. So out here I can't tell a difference. I have to actually zoom in quite a bit. Way in here. Even more. There we go. We're starting to see a difference. All the way in here. Look at my axes. Look how small these values are. Here's the value I'm trying to approximate. Again, the y coordinate. Here's my approximated value. That 0.09983333 repeating. So really small difference in that y value in the sign of 0.1 and its approximation. And again, this we did without trig at all. We didn't have to plug anything to a sine function, anything into a cosine function. We just needed to use our Taylor polynomial, which is pretty cool. So that's the idea of this approximation. Let's do a couple more examples. Let's do this one on page 5. So here we want to find the fourth degree Taylor polynomial for f of x equals e to the x about x equals 0. So the fourth degree Taylor polynomial. So again, first thing I'm going to do here is I'm going to write down my pattern, and I'm going to note that this is actually going to be the same structure as this, my third degree, except I'm going to have one more sum, one more piece of my sum here where I'm dealing with the fourth derivative, 4 factorial x minus a to the fourth, because I'm not finding the third degree polynomial, I'm finding the fourth degree polynomial. So let's write down this pattern again. This is f of a plus the first derivative at a over 1 factorial times x minus a to the 1 plus everything involving 2, the second derivative at a over 2 factorial times x minus a squared. Now everything involving 3, the third derivative at a over 3 factorial times x minus a cubed. And since I'm finding the fourth degree Taylor polynomial, I have one more piece here where I'm finding the fourth derivative at a over 4 factorial times x minus a to the fourth. So I'm finding a bit higher degree Taylor polynomial here, but the reason I'm doing that is in part because of how easy my derivatives are for this function. So again, what do we need here? We need our function value, we see that a couple times in here, plus 4 of its derivatives, and our a. So again, our a is the specific value of x that we're interested in terms of the specific point on our function. Here, we once again are doing this about x equals 0, which, like we said, means our a is 0. And because of that, this is another Maclaurin polynomial, right? It's the same thing as saying find the fourth degree Maclaurin polynomial for the function f of x equals e of x. So this is also a Maclaurin polynomial. All right, so let's look at our function here, and let's find our function and its first 4 derivatives. So f of x equals e to the x. Now remember, e to the x is that nice function where all of its derivatives are the same. If the function is just e to the x, the first derivative is also going to be e to the x. The second derivative is also going to be e to the x, because the derivative of e to the x is e to the x. And so on, all the way up to, in our case, we're stopping at the fourth derivative. So in other words, all of our derivatives are going to be equal to e to the x. And it also means that when we plug in our value of a of 0, f of 0 is going to be e to the 0, which is 1. And for this, we have f prime of 0 is going to be equal to f prime prime of 0, which is going to be equal to the third derivative at 0, which is equal to the fourth derivative at 0. And since all of the derivatives are also e to the x, this is going to be e to the 0 or 1. So in this case, my function at 0 and all of its first four derivatives at 0 or at 0 are all equal to the same thing, which makes our structure here a little bit easier. So let's plug everything in. First thing, my function value at a, we said that was 1. Plus, now let's look at our first derivative term. Our first derivative is also 1 over 1 times x minus a. A is 0 to the 1. That's this piece here. Let's do this piece. So the second derivative, which is also 1, over 2 factorial, 2 times 1, times x minus 0 squared. This piece, everything involving 3, the third derivative is also 1 over 3 factorial, 3 times 2 times 1, times x minus 0 cubed. And then finally, this last part, this is the fourth derivative. That's also 1 in this case, over 4 times 3 times 2 times 1 times x minus 0 to the fourth. Now it doesn't look like we have any terms that'll go straight to 0 here, but we can simplify this a little bit. This is 1 plus x minus 0 is x times 1 is x. This piece here, 1 over 2 times 1 is 1/2 times x squared. Our third, everything involving 3, that's our third derivative over 3 times 2 times 1, that's 6, times x cubed. And then finally here, 1 over 4 times 3 times 2 times 1. 4 times 3 is 12, times 2 is 24, times 1 is 24. So that's 1 over 24 times x to the fourth. And now again, just to put a visual to this, let me get rid of this stuff from the previous example. Here's e to the x in purple, looks like that. And here's the fourth degree Taylor polynomial that we just calculated. So we calculated this for values of x near 0. So notice, I got to zoom out a little bit, but it starts to, especially over here, not behave quite like the function in purple, but near 0, we've got really good similar behavior between these two functions. So we're not going to approximate anything with this one. I just wanted to give you another example, one where calculating the derivatives is not that much work. So you could do a higher order polynomial if you wanted to. But let's do one more where we do another approximation. So let's look at this one on page 6. We want to determine the second degree or the quadratic approximation for f of x equals 1 over x about x equals 2. And then we're going to use this to approximate 1 over 2.1. So, second degree Taylor polynomial. So what's our structure going to be? This is going to be the second degree Taylor polynomial. This is going to be f of a plus everything involving 1. first degree, or first derivative, sorry, not first degree, first derivative over 1 factorial times x minus a to the 1 plus everything involving 2, second derivative at a over 2 factorial times x minus a squared. And that's where I'm going to stop, right? It's just the second degree polynomial, second degree approximation. That's the end for the second degree, the quadratic approximation. I need my function and I need my a. So here we're interested in approximating about x equals 2. So in other words, that means our a in our expression is our 2. Which means this is not a Maclaurin polynomial, right? For Maclaurin, this thing has to be 0. Here it's not. So this is not also a Maclaurin polynomial. This is just a Taylor polynomial because our x is, or our a, is something other than 0. So it can't be a Maclaurin. All right, so here's our function. We want its value at a, and we want its first two derivatives at a as well. So f of x equals 1 over x. Now just to make our derivatives a little bit easier, I'm going to write this as an expression involving a power. 1 over x is the same thing as x to the negative 1, right? Which makes taking my first and second derivatives a little bit easier because then I can use the power rule instead of the quotient rule. So using the power rule, bringing the power out front, negative 1 times x to the negative 1 minus 1 is negative 2. So that's negative x to the negative 2. And I'm going to convert this back to a fraction because I am going to have to plug in my a value. And then once plugging your a value in, I think it's easier to do it in the fraction form. So converting this back to a fraction, this is negative 1 over x squared. Remember that negative exponent means the thing that's got the negative exponent is going to be under a 1, the denominator, 1 over that thing to the power. And then finally, my second derivative is going to be the derivative of this. So negative 2 times negative 1 is positive 2 times x to the negative 2 minus 1, which is negative 3. Rewriting that as a fraction, I have 2 over x cubed. Now, let's also plug in our a. So f of a, which is f of 2, is for our original function 1/2. For our first derivative, f prime of a is f prime of 2, which is negative 1 over 2 squared, which is negative 1/4. And then finally here, f prime prime of a is the second derivative at 2. 2 cubed is 8, so this is 2/8, or positive 1/4. So this. So let's plug these pieces into our structure of our second degree Taylor polynomial. F of a, we said, was 1/2, so that goes first. Then I have my first derivative, negative 1/4 over 1 factorial. 1 factorial is just 1, times x minus a to the 1. And here, remember, a is not 0, a is 2. So this is going to be x minus 2 to the 1. Plus, now everything involves 2. My second derivative, 1/4, divided by 2 factorial, which is 2 times 1, times x minus 2 squared. And rewriting that so it looks a little bit nicer, I have 1/2 plus negative 1/4 over 1 is just negative 1/4, so I'll say minus 1/4 times x minus 2, plus here I have 1/4 divided by 2. That's the same thing as 1/4 times, well, this is like 2 over 1. So the reciprocal of that is 1/2. That fraction's 1/8. Remember, when we're dividing a fraction by a fraction, we take the numerator fraction and we divide it by the reciprocal of the denominator. So 2 over 1 becomes 1/2, and this becomes 1/8 times x minus 2 to the 2. So this is my second degree or quadratic approximation or Taylor polynomial. All right, and we want to approximate 1 over 2.1. Now remember, the thing here is we want to look for what our x is. Remember, our original function here is 1 over x, right? So the x, the thing that we're plugging into this structure, is the 2.1. So that means in our Taylor polynomial, what we're going to do is every place we see an x, we're going to replace it with 2.1. So using this, I have 1/2 minus 1/4 times 2.1 minus 2 plus 1/8 times 2.1 minus 2 squared. And if I calculate that, I get 0.47625. Now, for something like an exam, we won't ask you for this. We might ask you for this structure, or it might show up as an option on a multiple choice. We won't have like this as a multiple choice option because we won't expect you to do all of this calculation by hand. If we're doing something with a Taylor polynomial, we might ask you for the structure like this, or how you would approximate this at 2.1, and where would you plug in the 2.1, that sort of thing. And just to see how close we were, what's the actual value of 1 over 2.1? Well, that's going to be 0.476190476 is the number of decimals my calculator printed out. So that's pretty good. 0.47625, 0.47619. Pretty good for a relatively easy polynomial to work with. So that's this idea of approximation. We're going to see kind of something like this in the next set of notes with Newton's method. The general idea behind it's going to be a little bit different, but we're still going to talk about this idea of using derivatives, using this instantaneous rate of change to find something or approximate something or get to something that we care about without having to use the original function, or at least use the original function in sort of a way that would maybe make things a little bit more complicated or a little bit less easy to work with when you're dealing with a bunch of calculations. So we'll see more of this sort of thing in the 6.3 notes.